For most of human history, we have believed a simple idea that progress moves forward, that knowledge accumulates, that each generation knows more than the last. But what if that story is wrong? What if thousands of years ago, human beings built machines so advanced, so precise, that even today, with all our technology, we still cannot fully rebuild them? Across oceans and deserts, buried beneath ruins and legends, are machines that should not exist, at least not in the time they were made. They do not fit the story we tell ourselves about the past, and their silence is unsettling. Because if ancient people could build these machines, then something vital has been lost. This is not a story about myths or exaggerated legends. This is a story about real objects discovered by archaeologists, studied by engineers, scanned by scientists, and still not fully understood. For the next 3 hours, we will journey deep into the ancient world to uncover 7 machines modern engineers still can't rebuild. Not because we lack intelligence, but because the past may have known things we forgot. To understand why these machines matter, we must first let go of a dangerous assumption that ancient civilizations were primitive. They weren't. They observed the skies with obsessive precision. They mastered stone, metal, and chemistry. They solved problems without electricity, computers, or modern mathematics. And sometimes they solved them better than we do today. Our journey begins not on land, but underwater. In the early 20th century, off the rocky coast of a small Greek island called Antikythera, sponge divers descended into the deep blue of the Mediterranean Sea. They were not searching for history. They were searching for sponges. Instead, they found a shipwreck. Scattered across the seabed lay bronze statues, pottery, coins, and fragments of wood, remains of a Roman cargo ship that had sunk more than 2,000 years earlier. Among these artifacts was something that appeared insignificant, a corroded lump of bronze. Cracked, broken, unremarkable, it was brought to the surface, cataloged, and nearly forgotten. But years later, when scientists examined it more closely, they noticed something strange. Inside the corrosion were shapes, not random shapes. Teeth, gears. What they had found would eventually be called the Antikythera mechanism, and it would force historians to rewrite everything they thought they knew about ancient technology. The device dates to around 100 BCE, at a time when historians believed complex machinery did not exist, at a time when the ancient world was supposedly limited to simple tools, pulleys, and levers. But this was something else entirely. The Antikythera mechanism was a compact system of bronze gears, over 30 of them, cut with extraordinary precision. Some gears were smaller than a coin, others meshed in layered complexity, stacked tightly within a wooden case. This was not decorative. It was functional. When reconstructed, scientists realized the device could predict solar and lunar eclipses decades in advance. It could track the cycles of the moon with astonishing accuracy. It modeled the irregular motion of planets, something that requires deep astronomical understanding. It even calculated the timing of major athletic events, including the ancient Olympic Games. In effect, this was an analog computer, built more than 2,000 years ago. What makes this machine truly disturbing is not just what it could do, but how early it appeared. The level of engineering required to design such gear systems was not believed to exist until medieval Europe. Mechanical clocks, which use similar principles, would not appear until over 1,000 years later. And yet, here it was, already perfected, already compact, already precise. Modern engineers have scanned the fragments using X-rays and advanced imaging. They have built digital simulations. They have attempted physical reconstructions using both modern tools and historically plausible methods. And still there are gaps. Some gears are missing. Some functions remain debated. Some inscriptions hint at features we do not fully understand. Even with modern technology, no reconstruction has perfectly matched the original size, precision, and functionality all at once. The more we study it, the stranger it becomes. This machine did not emerge suddenly. It implies a tradition, generations of experimentation, design, and refinement. You do not build something like this by accident, which raises a dangerous question. If this is the only example we've found, how many others existed? The ancient Greeks were obsessive observers of the sky. They tracked the movements of the sun, moon, and planets for centuries. They recorded cycles, anomalies, and eclipses. They developed mathematical models to explain what they saw. The Antikythera mechanism was not magic. It was applied knowledge, knowledge embedded in metal. And when the civilization that built it declined, that knowledge vanished. No manual survived. No workshops remained. No successors carried it forward. By the time Rome fell, the understanding required to build such a machine was gone. It would take humanity more than 1,000 years to rediscover similar mechanical complexity. This pattern repeats itself throughout history. A civilization rises. It solves problems in its own way. It builds machines suited to its world. Then it collapses, and its solutions disappear with it. The Antikythera mechanism forces us to confront an uncomfortable truth. Technological progress is not guaranteed. It can reverse, it can vanish, and it can leave behind artifacts that future generations struggle to comprehend. If ancient engineers could encode celestial mechanics into bronze gears, what else might they have built? What machines were melted down, lost at sea, or destroyed by time? And how many ancient inventions will never be rediscovered? Because we don't even know what to look for, the Antikythera mechanism is not just a machine, it is a warning. Because it tells us that human knowledge is fragile, and that the line between the ancient and the modern is thinner than we like to believe. In the next part of this journey, we will turn our attention away from the sea and toward the land, toward machines so vast, so precise, and so enduring that it still stands after 45 centuries. A structure built not to move, but to last forever, and behind it lies a construction system that modern engineers still cannot explain. The machine we turn to next does not tick, rotate, or hum. It has no gears, no moving parts, and yet it is one of the most complex machines ever built by human hands. It rises from the Giza Plateau, just outside modern Cairo. Silent, immovable, enduring. The Great Pyramid of Giza. It was already ancient when the Roman Empire was young. It was old when Jesus walked the earth. It had stood for more than 3,000 years before the first modern engineer ever laid eyes on it. And still today, one simple question has no agreed answer. How was it built? To understand why this question matters, we must first understand what the pyramid actually is. Not as a symbol, not as a monument, but as an engineered system. The Great Pyramid was constructed around 2560 BC, during the reign of Pharaoh Khufu. It originally stood 146 meters tall, making it the tallest man-made structure on Earth for nearly 4,000 years. It is made of approximately 2.3 million stone blocks. The average block weighs between 2 and 3 tons. Some blocks weigh over 80 tons. The total mass of the pyramid exceeds 6 million tons. And every one of those blocks had to be quarried, transported, lifted, positioned, and aligned, without iron tools, without wheels, without cranes, and without modern mathematics. Even more astonishing is the precision. The base of the pyramid is leveled to within a margin of error of just a few centimeters across nearly a quarter of a kilometer. The sides are aligned almost perfectly with the cardinal directions, north, south, east, and west, with an accuracy that rivals modern GPS measurements. This is not rough stone stacking. This is precision engineering. Modern engineers can measure the pyramid. They can model it. They can simulate construction scenarios using computers. But none of the proposed methods fully explain how it was actually done. The most common explanation is the ramp theory. The idea is simple. Workers drag stone blocks up massive ramps made of mud brick and limestone debris. But when engineers test this theory, problems quickly emerge. To lift the stones to the pyramid's upper levels, the ramp would have needed to be enormous, larger in volume than the pyramid itself. No physical evidence of such a ramp has ever been found. Other theories propose spiral ramps inside the pyramid, zigzagging paths, counterweight systems, or levering mechanisms. Each explains part of the puzzle. None explain all of it. And then there is the issue of time. According to historical records, the Great Pyramid was built in about 20 years. That means placing an average of one stone every 2 to 3 minutes, day and night, for 2 decades. This includes quarrying, shaping, transporting, lifting, and aligning each block. Even with modern machinery, this pace would be extraordinary. So what was a machine? The machine was not a single device. It was a system, a coordinated, large-scale construction process involving logistics, mathematics, labor organization, and mechanical innovation, none of which were recorded in surviving texts. The ancient Egyptians left behind detailed carvings of daily life. They documented religious rituals, agricultural cycles, and royal achievements. But when it comes to pyramid construction, they were silent. That silence is one of the greatest mysteries of ancient history. Some researchers believe the Egyptians used water as a mechanical aid, floating blocks along canals, using controlled flooding, or employing water-filled shafts to raise stones incrementally. Others propose that harmonic resonance, sound vibrations, played a role in moving or positioning massive stones, though evidence remains speculative. More conservative theories suggest lost lifting devices made of wood, rope, and stone, machines that decayed long ago, leaving no trace. But here is the problem modern engineers face. Even when they attempt to reconstruct these theories experimentally, the results fall short. The efficiency doesn't match. The precision doesn't hold. The scale becomes unmanageable. The pyramid's internal structure deepens the mystery. Inside are narrow shafts aligned with specific stars, chambers positioned with exact proportions, stress-relieving structures designed to distribute immense weight. This is not trial and error construction. This is planning, long-term planning. The builders knew exactly where every stone would go before the first block was placed, which means the Great Pyramid was not just built. It was designed as a complete system from the beginning. Modern engineers rely on blueprints, computer models, and structural simulations to achieve this level of coordination. The ancient Egyptians had none of these, and yet they succeeded. Even more unsettling is what happened after. The knowledge required to build a Great Pyramid appears to vanish. Later pyramids are smaller, less precise, less ambitious. The engineering capability peaked, and then declined. This directly challenges the idea that civilizations naturally improve over time. Instead, it suggests something else. That knowledge can be lost, that skills can disappear, that entire technological systems can collapse and leave behind only stone shadows. The Great Pyramid is not mysterious because it is old. It is mysterious because it is too good, too precise, too efficient, too well-planned. It stands as evidence of a construction machine we no longer understand, a system so effective that it was never repeated. And that leads us to another uncomfortable question. If ancient Egyptians could coordinate labor, materials, and mechanical processes on this scale, what other machines did they build that did not survive? Wood rots, rope decays, metal is melted down, stone remains. What we see today may only be the skeleton of a much larger technological world. The Great Pyramid does not just ask how it was built, it asks what else was possible, and whether modern civilization is truly as advanced as we believe. In the next part of our journey, we move forward in time to an empire that mastered not stone, but chemistry. An empire whose buildings still stand because their machines were not made of gears or wood, but of living stone that heals itself. An empire whose construction secret was forgotten for nearly 2,000 years. Next, we uncover the lost machine behind Roman concrete. Long after the pyramids were already ancient, another civilization rose, one that would stretch its influence across 3 continents. The Romans did not build for eternity. They built for function. Roads, bridges, aqueducts, harbors, cities, and yet, paradoxically, many of their structures have outlasted modern ones by centuries. The reason is not imperial power or slave labor. It is a machine hidden in plain sight, Roman concrete. To understand why Roman concrete is still one of the greatest engineering mysteries in history, we need to confront an uncomfortable reality. Modern concrete, steel-reinforced, scientifically engineered, standardized, is not meant to last thousands of years. Many modern structures are designed for a lifespan of 50 to 100 years. Some begin to crack within decades. Roman concrete, by contrast, has endured earthquakes, saltwater erosion, and time itself. Entire Roman ports still exist underwater, Their structure is stronger now than when they were first built. This is not an accident. It is a result of a lost process. The Romans did not use modern cement. Instead, they mixed lime with volcanic ash, known as pozzolana, and seawater. At first glance, this seems primitive. But when modern scientists studied Roman concrete under microscopes, they found something astonishing. Within the stone were microscopic crystals, formed not during mixing, but over time. As seawater seeped into the concrete, it triggered chemical reactions that caused new minerals to grow. These minerals filled cracks as they formed, strengthening the structure instead of weakening it. In other words, Roman concrete heals itself. This behavior directly contradicts modern building science, where water intrusion usually leads to decay. The Roman machine was not mechanical. It was chemical, and it was dynamic. But here's the problem. Even after identifying the ingredients, modern engineers struggle to replicate the process reliably. Small variations in ash composition, temperature, and mixing conditions drastically affect the result. The ancient Romans sourced ash from specific volcanic regions, places that no longer produce the same materials. The knowledge of which ash to use, how long to mix, when to pour, and how the environment would interact with the material was not written down in a single manual. It was embedded in practice. And when the Roman Empire collapsed, that practice disappeared. By the Middle Ages, the formula was gone. Medieval builders created massive stone cathedrals, but their concrete was inferior. Ports decayed. Structures weakened. It would take nearly 2,000 years before scientists even began to understand what made Roman concrete different. Even now, modern attempts to recreate remain experimental. Engineers can make concrete that lasts longer, but not concrete that improves with age in the same way. The Roman machine was perfectly suited to its environment. Harbors built in aggressive saltwater conditions became stronger over time, not weaker. This suggests the Romans understood their materials at a level that modern engineers are only beginning to rediscover. And yet, this knowledge was never passed down intact. It was lost not because it was useless, but because it was too embedded in a living system of builders, quarries, and environments. Once that system collapsed, the machine ceased to exist. The Roman example forces us to reconsider how we define technology. We often imagine machines as metal devices with moving parts. But some of the most powerful machines are processes, recipes, systems, methods. Roman concrete was one such machine, a machine that built an empire, a machine that modern civilization still struggles to replicate. And it raises a haunting question. How many other ancient technologies were not lost because they were impossible, but because they were too subtle to preserve? How many machines disappeared not with explosions or disasters, but quietly as craftsmen died and traditions faded? As we move forward in time, the next machine will challenge another modern assumption, that electricity is a recent discovery, because buried in the soil of ancient Mesopotamia is evidence that someone long ago may have learned how to produce it. In the next part, we uncover the mystery of the Baghdad batteries. Electricity feels modern. It powers our cities, our devices, our lives. We associate with wires, grids, and power stations, symbols of the industrial age. But what if the ability to generate electricity is far older than we believe? What if it existed and was forgotten? In the 1930s, just outside Baghdad, archaeologists uncovered a strange collection of objects buried beneath ancient ruins. At first, they appeared ordinary. Small clay jars, copper cylinders, iron rods. Individually, they seemed unremarkable. Together, they formed something unsettling. When modern researchers recreated the arrangement and filled the jars with acidic liquids like vinegar or wine, the devices produced an electrical charge. Low voltage, but real. These artifacts became known as the Baghdad batteries. They date to roughly 200 BCE to 200 CE, nearly 2,000 years ago. And they raise a question that refuses to go away. Why did they exist? No ancient text described them. No diagrams explain their purpose. Yet their design is deliberate. The copper cylinder acts as a conductor. The iron rod serves as an electrode. The acidic liquid completes the circuit. This is not accidental. Someone understood the basic principles needed to produce electrical current. But here is where the mystery deepens. Electricity by itself is not useful unless it is applied. So, what was it powering? One leading theory suggests electroplating. Using electrical current, ancient craftsmen could coat objects, especially jewelry, with thin layers of gold or silver. This would allow them to produce high-quality decorative items with minimal precious metal. Some ancient artifacts do show signs of plating that are difficult to explain using purely chemical methods. Another theory proposes medical or ritual uses. Electric stimulation can cause muscle contractions and sensory effects. Perhaps the batteries were used in healing rituals or religious ceremonies, producing sensations interpreted as divine. Others suggest the devices were part of alchemical experimentation, early attempts to understand the hidden forces of nature. But none of these theories are proven. What we do know is this. The Baghdad batteries were not isolated curiosities. Similar jars have been found in multiple locations, which implies this was not a one-off experiment. It was a practice, and yet the knowledge did not survive. There is no evidence of wires, grids, or large-scale electrical infrastructure. If electricity was used, it was likely small-scale, specialized, and controlled, which may explain why it left so little trace. But that explanation leads to another unsettling idea. Ancient technology did not always aim for mass production. It aimed for precision. And when the social or cultural need vanished, so did the machine. Modern engineers can recreate the Baghdad batteries easily, but they cannot answer the most important question. Why? Why develop electrical technology without expanding it? Why leave no written record? And why allow the knowledge to disappear completely? Perhaps the batteries were part of a technological path that never fully developed, or perhaps they were intentionally limited, because technology does not exist in isolation. It exists within culture, and not every civilization chooses the same direction. The Baghdad batteries remind us that invention is not destiny. A technology can exist and then be abandoned. As we continue our journey, we move east, toward a civilization that solved a problem most travelers still struggle with today: how to know where you are without a compass. In the next part, we uncover the mystery of the south-pointing chariot. For most of human history, finding direction was a matter of instinct, landmarks, and the stars. Lose the stars, lose the landmarks, and you were lost. But in ancient China, engineers built a machine that solved this problem in a way that still astonishes modern minds. It did not rely on magnets. It did not rely on the sky. It did not rely on memory. No matter how the vehicle turned, a figure mounted on top always pointed south. This was the south-pointing chariot. Its earliest versions are believed to date back more than 1,700 years, though Chinese texts suggest even earlier origins. It was not a myth, not a metaphor, but a real mechanical device described in historical records. And yet, no original chariot survives. Only words remain. To understand why this machine is so extraordinary, we must understand what it did, and what it did not do. The south-pointing chariot was not a compass. It did not use magnetism, which was not widely applied for navigation at the time. Instead, it relied entirely on mechanical ingenuity. Inside the chariot was a system of gears, specifically a differential gear system. As the chariot turned left or right, the wheels rotated at different speeds. The internal gearing compensated for these changes, keeping the pointer aligned in a constant direction. This is the same principle used in modern vehicle differentials. And here's the shocking part. Differential gears would not appear in European engineering until the 18th century, more than 1,000 years later. Modern engineers understand how differential gears work. But reconstructing the south-pointing chariot from historical descriptions has proven surprisingly difficult. The texts are incomplete. The diagrams are vague. The tolerances required for smooth operation are extremely tight. Small errors cause the pointer to drift. Modern reconstructions often fail over long distances or rough terrain. The ancient versions, according to historical accounts, worked reliably, which suggests a level of craftsmanship and mechanical understanding that exceeds what we usually attribute to the era. The south-pointing chariot was not just a curiosity. It was used by emperors, generals, and officials. It played a role in ceremony, authority, and control. Direction, in ancient China, was deeply symbolic. South represented order, balance, and legitimacy. A machine that could always point south was more than a navigational tool. It was a symbol of harmony between technology and the cosmos. And yet, like so many ancient machines, the knowledge did not survive intact. The chariot disappeared. The craftsman who built it died. The tradition faded. Later generations remembered that it existed, but not how to build it. Today, engineers can propose models. They can simulate mechanisms. But they cannot say with certainty which design the ancients used. The exact machine is lost. This raises a profound point. Technology does not always evolve by improvement. Sometimes it evolves by forgetting. A solution can exist, work perfectly, and then vanish, not because it failed, but because it was no longer needed or no longer understood. The south-pointing chariot reminds us that ancient engineers solved problems differently. They did not rely on invisible forces, like magnetism. They relied on physical logic, motion, balance, cause and effect, and they encoded that logic into machines that required no external power. As we move deeper into our journey, the next machine will challenge another modern assumption, that ancient metallurgy was crude, because standing silently in the heart of India is a structure that refuses to rust after more than 16 centuries. In the next part, we explore the mystery of the Iron Pillar of Delhi. In the center of modern Delhi, surrounded by traffic, pollution, and centuries of human activity, stands a silent anomaly. It is not massive like a pyramid. It does not move like a machine. It does not glow or spark. And yet, it defies one of the most basic laws of metallurgy. Iron rusts. Exposed to air and moisture, iron corrodes. It flakes. It weakens. It returns to the earth. Except here. The Iron Pillar of Delhi has stood for over 1,600 years, exposed to monsoon rains, extreme heat, and urban pollution, and it is barely rusted. To understand why this is extraordinary, we must understand what the pillar is. It stands over 7 meters tall and weighs more than 6 tons. It was erected during the reign of the Gupta Empire, around the 4th century CE. At the time, iron production was limited. Smelting required precise temperature control, careful handling of materials, and deep practical knowledge. The pillar was not cast. It was forged. Large pieces of iron were heated, hammered, and welded together, a process that becomes increasingly difficult as the size of the object increases. Modern blacksmiths struggle to reproduce this technique on such a scale without advanced equipment. But the true mystery lies in the metal itself. When scientists analyzed the pillar, they found it contains an unusually high phosphorus content and extremely low sulfur and manganese. This composition is not accidental. It is a result of a specific smelting process that avoided lime and relied on charcoal. Over time, the phosphors reacted with oxygen and moisture to form a thin, invisible protective layer on the surface of the iron. This layer, stable and self-renewing, prevents rust from spreading. The pillar does not resist corrosion through coatings or treatments. It resists corrosion through design. This is not just metallurgy. It is material science. And here is the unsettling part. While modern science can explain why the pillar resists rust, reproducing it naturally, without modern chemical treatments, remains extremely difficult. The ancient process required precise control over or selection, furnace conditions, and forging techniques. These were not written down. They were passed through experience. When those traditions ended, the machine ended with them. The Iron Pillar forces us to rethink what ancient craftsmen were capable of. They were not blindly experimenting. They were observing patterns, refining techniques, and embedding knowledge into materials. The pillar is not just a monument. It is a lesson preserved in metal. A lesson that modern engineers had to rediscover through analysis and reverse engineering. And yet, even now, we struggle to replicate at scale. This is a recurring theme. Ancient machines were often perfectly adapted to their environment. They did exactly what they needed to do. No more, no less. When the civilization that understood them faded, the machines remained, but their logic was lost. As we approach the final machine in our journey, We move across oceans and mountains to a civilization that masters stone in a way that still resists explanation. A civilization without iron tools, without wheels, without written language. And yet, they built structures that modern engineers still struggle to match. In the final part, we uncover the mystery of Inca stonework. High in the Andes Mountains, where the air is thin and the ground trembles without warning, stand walls that should not exist. They are not smooth. They are not uniform. They are not held together by mortar. And yet, they have survived for centuries. Earthquakes that reduce modern buildings to rubble have passed through them without effect. This is a machine of the Inca, not a device, not a tool, but a method so precise, so refined, that even today it defies full explanation. The Inca Empire rose rapidly in the 15th century, stretching across much of western South America. It was a civilization without iron tools, without wheeled transport, and without a written language. By modern standards, they should not have been able to build what they did, but they did. At sites like Sacsayhuaman, Ollantaytambo, and Machu Picchu, massive stones, some weigh more than 100 tons, were cut, shaped, transported, and fitted together with astonishing precision. No mortar binds them. Instead, each stone locks into the next like a three-dimensional puzzle. The joints are so tight that a razor blade cannot be inserted between them. This level of precision is difficult even with modern power tools. So how did the Inca do it? The stones were not carved into simple blocks. They were shaped into complex, irregular forms, each stone custom-fitted to its neighbors. This method distributes stress evenly throughout the wall. When an earthquake strikes, the stones shift slightly, absorbing the energy, then settle back into place. The wall moves, but it does not fall. Modern engineers understand the physics behind this behavior. What they do not understand is how the Inca achieved it so consistently. There are no surviving tools capable of such precision, no written manuals, no step-by-step instructions. Some researchers suggest the Inca used harder stones as hammer tools, combined with sand and water for grinding. Others propose lost techniques involving heating and cooling or chemical softening of stone, ideas that remain controversial and unproven. What is clear is this: the Inca did not rely on brute force alone. They relied on patience. Each stone could take months to shape. Workers repeatedly placed a stone, removed it, shaved off tiny imperfections, and tried again, over and over, until it fit perfectly. This required coordination, planning, and an intuitive understanding of geometry and stress that rivals modern engineering. Even more remarkable is the scale. These techniques were applied not just to temples or palaces, but to entire cities. Roads, terraces, fortresses, and homes all followed the same principles. This was not experimental. It was standardized. And then, almost overnight, it ended. When the Spanish arrived, the Inca Empire collapsed with devastating speed. Disease, conquest, and cultural destruction erased much of their knowledge. The stone walls remained. The method did not. Modern builders can imitate the look of Inca stonework using lasers and power tools, but they struggle to reproduce the same seismic resilience using only ancient methods. The Inca machine was not written down. It lived in the hands and minds of craftsmen. When they were gone, the machine vanished, and with it, a way of building that modern civilization still struggles to fully replicate. We have now traveled across continents and centuries, from bronze gears beneath the sea, to pyramids in the desert, to living concrete, forgotten electricity, mechanical navigation, rust-proof iron, and earthquake-proof stone. Each machine tells the same story. Ancient civilizations were not waiting for progress. They were already experimenting, innovating, and mastering their world. And yet, much of that mastery was lost. Which brings us to the final question. If so much knowledge disappeared in the past, how secure is our own? We assume our technology will endure, but history suggests otherwise. Civilizations fall, systems collapse, knowledge fragments. What would remain of us thousands of years from now? A few structures, a few artifacts, fragments without context. Would future engineers understand our machines, or would they look at our ruins and wonder how we ever built them? The past is not primitive. It is unfinished. and it is still speaking to us through machines we can touch, but not fully recreate. If you want to keep exploring forgotten technologies of ancient history, subscribe to Ages Past, because the past does not disappear. It waits, in stone, in metal, in silence,